JAMB 2026 candidates, welcome to the lecture today, where we are going to continue from where we left off. So if you are taking this lecture, get your pen and your notebook to jot down anything you understand in this lecture, because you are going to need them for subsequent revision when it's 2-3 weeks to your JAMB UTME. Let's look at the propagation of sound wave. You know, sound wave is a very unique wave. Necessity for a material medium. You know, the sound wave requires a material medium. Let's look at the necessity for a material medium. Sound wave is a mechanical wave. It requires particles to vibrate and transfer energy. So the sound wave is a mechanical wave, like we learned in the previous lecture, and it requires a material medium. It requires a particle to vibrate and transfer energy. A particle is required, and it cannot travel in a vacuum. Sound wave cannot travel in a vacuum. It cannot travel in an enclosed space, okay? It does not travel in a vacuum. So now let's look at the speed of sound in different media. Speed of sound in different media. The first we have here is in solids, and it is the fastest. Sound has its fastest speed or velocity in solid, and the speed of sound in solid is 5,000 meters per second in steel, for example, steel. Then let's look at the speed of sound in liquids. Liquid is slower than solid but faster than gases, okay? And it's equivalent to 1,500 meters per second in water. Let's look at sound in air. The speed of sound in air is the slowest. It's much slower, the slowest. And it's equivalent to 340 meters per second at room temperature. Speed increases with density and elasticity of medium. So for sound wave, speed increases with density and elasticity of medium. For example, solid has a high density and is highly elastic. That's why the speed of sound wave is highest in solid. You can see liquid, second in command. Liquid has is more dense than air, and it's more elastic than air. That's why sound is faster in liquids than air, and so on and so forth. So ensure to learn all the speeds of sound in various medium. In solid we have 5,000, in liquid we have 1,500, and in air we have 340, all in meter per second. Effect of temperature and pressure. Speed of sound in air increases with temperature. The speed of sound in air increases with temperature. Pressure has negligible effects. So pressure has little to no effect when it comes to sound. So pressure has negligible effects, little to no effect when it comes to sound. But speed of sound increases in air with temperature. When the temperature is high, the speed of sound is also high. Since both pressure and density changes proportionally. So the pressure of a system increases density. So they change proportionally. That's why pressure does not necessarily affect the quality of sound or the intensity of sound. Now, let's look at the reflection of sound. Sound waves can reflect off surfaces. For example, echo. You have to understand the meaning of echo. Echo can be defined as the reflection of sound heard after 0.1 seconds or more. Okay, the reflection of sound heard after 0.1 seconds or more. Okay, you hear it. It's just that short reflection you hear when the sound has been put across. You hear it 0.1 seconds after that sound has been put across. So if I say hey now, for example, you are going to hear the reflection. That's reflection of the sound. This that reflection of this sound, you are going to hear it as a reflection 0.1 seconds after I shouted hey. So the distance is greater or equal to 17 meters in air. The distance is greater or equal to what? 17 meters in air. So the distance of this reflection is greater or equal to 17 meters in air. Echo and reverberation are two related sound concepts, okay, especially when you talk about reflection of sound in a surface or reflection of sound. But reverberation has a slight difference from echo, and so let's understand it. Reverberation is multiple reflections of sound wave causing propagated sound. So it causes multiple sound, multiplication of sound. So you hear hey, you are going to hear something like hey, go, you are going to hear go. That's reverberation. But echo is just a reflection. But reverberation is multiple reflection of sound wave, which causes what? Propagation or propagated sound. It causes propagation of sound wave or propagated sound. That's why you hear wait. Go. Multiple reflections. Let's look at the applications of echo and reverberation. Echo, distance measured. You know, echo has to do with distance. Greater or equal to 17 meters, like we discussed. Is applied in sonar and medical use, such as in ultrasound. That's why they call it echo, echogram, okay, or echocardiogram, okay, and so on and so forth. So echocardiogram is the visualization of the heart with specialized ultrasound. There's a specialized probe for it. So echocardiogram. So echo is that reflection of sound wave, the sound wave, minute sound wave given off by the tissue. or the heart itself. That's what the medical professional or the diagnostic professional uses as a guide to visualizing the heart. So medical use it in ultrasound and in sonar. You also use echo to measure distance. When you are still hearing echo, you know that the distance of the sound or the distance of the source of that sound is not so far from you. Greater or equal to 17 meters. Okay. So reverberation, what is reverberation used for? Or where do we apply reverberation? It's used in music hall for richness of sound. Like when you go to the clubhouse, you hear the way the music did the band now, boom, 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 because everywhere is covered. They cover everywhere, so that there's going to be multiple reflection of this sound wave. When you hear boom, 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 it's going to be boom, 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 boom inside the clubhouse. That's one of the applications of reverberation. In fact, it's the most common application of reverberation. Now, let's look at the advantages of echoes and reverberations. The advantages is its usefulness in navigation, medical diagnosis, and architectural acoustics. Okay, in navigations, like when you are using an instrument, navigating with an instrument, like in medical practice where you use instruments to, such as instruments with optic fiber or fiber optic instruments to trace something in any of the systems, digestive system or any system. Okay, you use it for navigation. You also use it for medical diagnosis, like for in ultrasound or echocardiogram or echo ultrasounds, and you use it in architectural acoustics. Okay, so what are the disadvantages of echoes and reverberations? One is it causes distortion of speech. The speech no go clear where. Two is noise pollution. That boom 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 way they hear for club, boom 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 is noise pollution. Now the way reverberation they cause noise pollution. If you hear you shout, it's noise pollution. You are disturbing someone else because of that echo, that multiplication of sound or that reflection of sound. Okay, it also causes unclear sounds in hall, just like in club. The sound when you talk for club, now make people they talk for club, they know they hear. You need to hear the person they talk for inside here. That's the way you put for there, go come out and person go there and say, you say that's the way you put for there, go come out and person go there and say, distortion of sounds due to reverberation. It can also be caused by echo, distortion of sound. When you shout, hey, you are still hearing another hey from the farther side. That's going to cause a kind of distortion. You know the one when you hear. Okay, so these are the disadvantages of echoes and reverberation. Let's now look at the characteristics of sound wave. 1. Noise versus music notes. Let's understand the difference between noise and music note. First of all, the first characteristic of noise is that it's irregular. I explained this before, that noise is not arranged. It's not directional like musical notes. It's irregular, it's unpleasant, it's an unpleasant vibration. It's not, you don't like it, okay? Then music note is regular, it's directional, okay? It's periodic vibration producing harmony. So it's periodic vibration, it's timed, it's sequential, okay? Producing harmony. Harmonies are music notes that come together to form a reasonable sound. That's harmony. They are in harmony. They are in unity. Music notes or sounds, music notes or sounds that is brought together to form an appealing note. Okay, that's harmony. Now let's look at definition of various terms when it comes to sound wave. We have pitch here, and pitch depends on frequency. For pitch to operate, for pitch to function, it has to depend on frequency. And high frequency equals high pitch. Put this in your mind, though. You will see all these things for your JAMB-REPEATED hall. You will see an inside examination hall. High frequency equal to high pitch. If the frequency is high, the pitch will be high. You know the pitch of sound. When you increase that pitch of the sound, that's the pitch of the sound. So the height of the frequency. So let's look at the intensity. Energy per unit area per unit time. So energy per unit area per unit time is intensity of sound. So it depends on the amplitude. So unlike pitch that depends on the frequency, the intensity of sound depends on the amplitude. So the pitch of sound is the maximum frequency in a sound waveform. Okay, the maximum frequency attained. That's why when you have high pitch of a music note in any sound, you are going to see that the frequency there is higher. Okay, that's why the higher the frequency, the higher the pitch. But intensity is dependent on amplitude. Okay, so let's look at loudness. Loudness, human perception of intensity. How do you perceive the intensity of sound? That's loudness. Do you perceive it as high? Well, if you perceive it as high, it is high. Yes, humans, you perceive it as low, the sound is low. So how you detect sound? You detect it as either high or low. Okay, that's loudness. Okay, that's loudness. How humans detect the intensity or how they perceive the intensity of sound wave. That's loudness. Then let's look at quality, also known as timbre. Quality is also known as timbre, sound quality. It distinguishes sounds of same pitch and loudness from other sources, depending on overtones. Okay, so the quality of sound helps you distinguish between sounds. Okay, is this sound from this object? Is this sound from this object? So the quality of sound helps you distinguish. If a glass gets broken now, for example, and a plastic cup fall on the ground, you can easily differentiate without seeing them that this sound was from a broken glass. This sound was from maybe a plastic something or something that just fell. but it's a plastic, but that's not glass. This one is glass. So timbre, or the quality of sound, helps you distinguish, okay? And it depends on overtone. So just know the three. Pitch depends on frequency. The higher the what, the frequency, the higher the pitch. Intensity depends on what, the amplitude. Okay, the higher the amplitude, the higher the intensity. The loudness is the perception of the sound intensity by humans. Okay, then quality of sound or timbre depends on overtones. Okay, overtones. Now let's look at the application of these. Okay, let's look at the application of these, the characteristics of sound wave, to the making of musical instruments, or the principle of music instruments, how they work. Let's look at how those characteristics of sounds are applied in musical instruments. The first we have here is pitch controlled by length/tension of string. Okay, the pitch of the sound the string is going to give is controlled by the length and the tension of the string. So the length of the string determines its pitch. The tension of the string determines the pitch that the sound from the string is going to appear in. So the tension and the length of the string determines the pitch. So the longer the string, the lower the pitch. The shorter the string, the higher the pitch. But the higher the tension of the string, the higher the pitch. The lower the tension of the string, the lower the pitch. Let's look at loudness. Loudness is controlled by amplitude. We said that before. And the quality of sound is determined by harmonics produced. We already know what harmony is. I explained what harmony is. So when you bring different music notes together, not with almost similar frequencies, you form a harmony, or a harmonic music note. Okay, so harmonics and overtone. Let's understand these two concepts: harmonies and overtone. Harmonics is integral multiples of fundamental frequency. Integral multiples of fundamental frequency is like, it means like you bring multiple fundamental frequencies together. Integration of multiple fundamental frequencies together. When you say fundamental frequencies, you mean fundamental frequencies or music notes that are close. Okay, they have close frequencies. You bring them together. But overtone, what is overtone? Higher frequencies produced along with fundamental. Higher frequencies produced along with fundamental. Higher frequencies. So the frequencies are higher in overtone. Okay, vibrating string and air column produces harmonics. Okay, vibrating strings and air columns produces harmonics. Okay, that's why the vibration from a string is harmonic. I love that harmony. It's harmonic, beautiful. So higher frequencies produce along with fundamental. So you know that even when you give a harmony, okay, there are some of the notes that are higher, there are some of the notes that are lower. So the higher ones inside is called overtone. Okay, overtones. Now let's look at resonance. What is resonance? When frequency of external force matches natural frequency of system. That's when resonance occur. Resonance occur when what? When the frequency of external forces matches what? The natural frequency of the system. The frequency of external forces, the atmospheric force, matches the force in the system, matches the frequency in the system of that musical instrument. That's when resonance occur. And resonance is like the sound made from a hollow material or a hollow object. Resonance, an air-filled object. The sound generated by an air-filled object. And the amplitude increases greatly. In resonance, amplitude increases greatly. Please take note of this. Example of resonance: tuning fork with resonance box. You air-filled. Resonance is the sound gotten from an air-filled body. So the resonance of what? Tuning fork with what? The resonance box. These are resonance. Okay, tuning fork with resonance box. When you put the tuning fork on a resonance box, you are going to notice resonance. Organ pipes, air-filled organ pipes. You also have a breaking of glass by loud sound. So all these are examples of resonance. JAMB says we should be able to give examples of resonance. Okay, so know these and know peace. Frequency of notes in air column. The first we are looking at here is the closed pipe. I say JAMB like to repeat this question. This frequency of notes in column, closed pipe and open pipe. You have the second harmony, you have the fourth harmony, you have the third harmony. But let's look at what we have here as specified by JAMB in their syllabus. They recommended all this we have here. Okay, so frequency of note in air column, we have the closed pipe and the open pipe. Let's look at the closed pipe. Closed pipe, fundamental frequency F is equal to V over 4L. This is the formula for the closed pipe. If you're using closed pipe harmony, if you look at the question and the question says a closed pipe, for closed pipe, see how to spot the difference between a closed pipe and the open pipe harmony. In a closed pipe, harmonics is going to open out to something. Maybe you are going to see it like this. Okay, like this. Here is going to be open. Nothing is going to block inside. Okay, it's going to be hollow. Nothing is going to block it. But open pipe harmonics, you are going to see something that will be inside. There will be something inside that blocks it. It might be cross inside. There might be a cross line like this that is blocking it inside. But something will block it. It will not be so open. It will not be open. Okay, so that's the difference between closed pipe and open pipe harmony. So this one is the formula for the open pipe harmony, where L is for the length, V is for velocity. Then open pipe harmony, fundamental frequency F is equal to what? V over 2L. Okay, just know that closed pipe is V over 4L, open pipe is V over 2L. As simple as that. L is length and V is equal to what? Velocity. So if they ask you what's the fundamental frequency of so pipe, they'll just show you the diagram there. You first of all check if it's an open. First of all, you check if it's an open pipe or a closed pipe. Okay, so use any of the mashing formulas to solve for the fundamental frequencies. Okay, where length L is equal to length of pipe, V equal to velocity of sound, like I explained earlier. Now that we have understood the propagation of sound wave, let's now try some JAMB must repeat questions to further test the knowledge we've acquired so far. JAMB must repeat questions. Question 75. Sound cannot travel through what? A. Solids. B. Liquids. C. Gases. D. Vacuum. What's the answer? Drop the answer in the comment section. Question 76. The speed of sound is greatest in A. Air. B. Water. C. Still. D. Vacuum. What's the answer? Drop the answer in the comment section. Question 77. An echo is heard when the reflecting surface is at least how far away from the listener? Take speed of sound in air equivalent to 340 meters per second. What's the answer? A. 8.5 meters. B. 17 meters. C. 34 meters. D. 68 meters. What's the answer? Drop the answer in the comment section. This question is very, very easy if you know the concept of echo. Very small concept of echo that I just taught. So pick the answer among the options. Drop the answer in the comment section. Question 78. Which of the following is a characteristics of musical notes but not of noise? A. Irregular vibrations. B. Regular periodic vibrations. C. Unpleasant sound. D. Random frequency distribution. What's the answer? Drop the answer in the comment section. Question 79. The fundamental frequency of a closed pipe of length 0.5 meter is take speed of sound equal to 340 meters per second. A. 15 hertz. B. 340 hertz. C. 680 hertz. D. 85 hertz. This question is so easy if you've taken my lecture or you've read my material. What's the answer? Drop the answer in the comment section. Question 80. The pitch of a sound depends on dash. A. Amplitude. B. Frequency. C. Intensity. D. Loudness. What's the answer? If you have taken my lecture or you have this my material you can see on the screen, this question is so easy. You wouldn't spend more than 2 seconds answering this question. Drop the answer in the comment section. Alright, this material you can see on your screen is the material containing all the JAMB topics tailored from JAMB syllabus. So it's very short and straight to the point. With JAMB must repeat past questions to test the knowledge you acquire as you go. So if you need this file, send me a DM. The cost is 1K only. I can't wait to give you access to this material. Look at what you are getting. Look at what you are getting. Look at what we end here for jokes. JAMB 2026 candidates. Peace out. Peace out.